Alright, so in this video, I will be using Python to simulate the height of the three tanks from the last part of the video. So here is the picture of all of our equations from the first part, and we are going to use Python and simulate the heights. So what I'm going to start with is I have my import statements here. We have numpy. These will be used in plotting the heights of the tanks, and then we'll use solve IVP to solve our differential equations. So I'm going to start with defining our constants. So we have our cross-sectional areas of the three tanks, which are equal to 0.5 meters squared, 1 meter squared, and 2 meters squared respectively. So we also have the initial fluid heights. So the initial height of tank 1, tank 2, and tank 3 are 0.5, 1, and 2 meters respectively. And then we also have the proportionality constants for the flow rates, right? From our whiteboard, it was our alpha terms. And in this case, the proportionality constant for the flow rate between 1 and 2, and tanks 2 and 3 is 0.1. It is also the same for the flow rate out of tank 3. So I'm just going to define it as 1 alpha as 0.1. So now let's define the function that we will pass to our solve IVP. And since we're passing it to solve IVP, we need to start with a input of time, and then we will have our vector of unknowns. So the vector of unknowns will be the heights of the three tanks, the liquid height of the three tanks, and we just need to code in our equations from the whiteboard, right? So there will be these 4 flow rate equations, and then we'll use these differential equations to calculate the change in height. So the flow rate between 1 and 2 was defined as the sine of the difference between the height of tank 1 and the height of tank 2 times our proportionality constant alpha times the absolute value of the difference between the height of tanks 1 and 2 to the 1/2 power. And then the flow rates between tanks 2 and 3 are similar, but we will use the difference between the height of tank 2 and the height of tank 3. So there is the flow rate between tanks 2 and 3, and then we have our flow rate out of tank 3, which is just our proportionality constant alpha times the height of tank 3 to the 1/2 power. And we also have our flow rate in, which we are controlling using a proportional control. So it will be our proportional gain times our set point of tank 3 minus the actual height of tank 3. So then I'm going to go up here and define our set point, which is 4 meters. And our proportional gain is 0.1 for this problem. So now we can return the equations for the change of heights. So how I'm going to do that, I'm just going to use these 3 differential equations and divide by the cross-sectional area. So that way we just have the change of height, the rate of change of height on the left side. So we will have the negative flow rate between tank 1 and tank 2 over the cross-sectional area of tank 1. Then we will have the flow rate into tank 2 plus the flow rate between tank 1 and tank 2 minus the flow rate from tank 2 to tank 3. And this will all be over the cross-sectional area of tank 2. And then for our third equation, we will have the flow rate into tank 3, so Q23, minus the flow rate out of tank 3, which is Q3, and this will be divided by the cross-sectional area of tank 3. So these three equations will give us the rate of change of height 1, height 2, and the height of tank 3. So now we can go ahead and use solve IVP. So to use this, we will supply the function which we just created, right hand side. We will provide a time span, so from 0 till Tn, and I'll go up here and define how long we want to run our simulation. So I'll start with 50 seconds. We might need to adjust that. And then we need to supply our initial values, which is just the initial height of the liquids in tank 1, 2, and 3. We'll have our method as redow, which is just the method for solving these differential equations. I'm using this method because it is one of the more accurate methods, but it's also a little slower, but it's really not a big deal in this case. And then we'll also set the dense output equal to true. So this will allow us to evaluate our solution at many different times, which will be useful for graphing. So we'll go ahead and run this. And there we go. This is the output. So what we want is this solution objects, which, like I said, we'll be able to pass time to it, and it will give us the solution for our differential equations at any time. So we need just the solution attribute, which we'll get using .sol, and I will just call this object my solution. So now we're ready to graph these. So I'm going to start by creating a time for plotting purposes using linspace, and it will be from 0 to our end time for our simulation. I'll go by about 500 points, and then we will define the heights. So these will just be our solution evaluated at our times that we're going to plot. Now we're ready to plot. So I'll define our first figure. And we'll add a scatter. And so I'm going to graph each height on the same set of axes. So we kind of can see the same set of axes, so we can see how they're interacting and how they're changing over time. So we'll use add scatter. Our x will be our time. Our y will be the height of tank 1. I will set the mode to lines to give us a nice smooth line, and then I will name it height 1. And so I'm going to use this, and we'll copy and paste it twice, and we'll use it to graph the height of tank 2 and the height of tank 3. So now I'm going to run it and see how it looks. Pretty good, right? So down here we have tank 3, this blue line is tank 1, and this red line is tank 2. So we haven't quite reached steady state, so I'm going to increase the simulation time to maybe we'll double it and see if this is okay. So we're getting there, right? Still not quite at steady state. Maybe we're just right before it. So I'm going to go ahead and double our simulation time again. And there we go, we've reached steady state. So let's see, we set the height of tank 3 to be 4, but if we see at steady state, it's only about 2.5. So the reason for this is because we are using a proportional control. So these actually have quite a bit of error, And one of the ways to get closer to our set point is to increase our value for the proportional gain. So this will increase the amount of fluctuation. So you see it overshoots multiple times before reaching our set point, but you can see we're much closer. So now it's at 3.8. But the problem specified 0.1, so I'm gonna go ahead and change that back. And there we have the three heights of the tanks.